Hello, my darlings. Okay, so today we're going to review extrema and concavity. But before we get to that, let's remind ourselves what a critical point is. So a critical point of f of x is a point where the derivative is 0 or where the derivative does not exist. We also had a function that says if a function has a relative extremum, meaning a max or a minimum, at an x value c, then the derivative at c equals 0, or the derivative at c does not exist. Remember, these are the critical points. So if there's going to be a max or a min, it's going to happen at the critical points. But just because we have a critical point does not mean we'll have a max or a min. This only works in one direction. If you have a max or a min, then you know you have a critical point. Every critical point is not necessarily a max or a min. We also have another term, the point where the concavity changes is called a point of inflection, or an inflection point. So if the graph changes from concave up to concave down, that is your point of inflection, right where it changes. Okay? So far, so good? Okay. So next, I want to talk about the fact that there really are only 4 types of curves that make up any nonlinear graph. No matter what the function is, as long as it's not linear, it's made up by combining these 4 types of curve. And if you look at the curves, concave down and increasing, concave down and decreasing, concave up and increasing, concave up and decreasing. If you put them all together, you would have a circle. So it's easy to remember the 2 types, okay? So I want you to try to remember that. Now, when the function is concave down, that will tell us that our second derivative is negative, okay? It's also going to tell us that the first derivative is decreasing. And again, over here, where on this piece, the graph is concave down, right? It's curved down in both of these cases. Our derivative is less than 0 or negative, and we also know that f prime of x is decreasing. The slopes here are decreasing because notice the slopes of these tangent lines here, they're getting less steep, so they're getting smaller. Here, they're getting more steep, but they're getting more steep in the negative direction, so the values of the slopes are indeed getting smaller. Let's look at the third type. Now we're looking at a graph that is concave up. And if we're concave up, our second derivative is positive, and our first derivative is increasing. And here, again, concave up, our second derivative is positive, our first derivative is increasing. Now, if we go back to the first curve and we look at the fact that the function is increasing, if our function is increasing and going up, that means that our derivative must be greater than or equal to 0. Okay? When our function is decreasing, our derivative is less than or equal to 0. Here in the third case, we also have our function decreasing, which means our derivative is less than or equal to 0. And again, in the fourth case, we have our function increasing, which means our derivative is greater than or equal to 0. Okay? Those are the only 4 types of curves in existence. We're going to look at the first derivative test and relative extrema. So, for the first derivative test, if a critical point of f of x is a relative minimum only if f prime of x changes from negative to positive, because if the derivative is negative, the function's decreasing, and then when the derivative is positive, the function's increasing, which means that turning point, which is our critical point, is a minimum, okay? Now, a critical point is a relative maximum if f prime of x changes from positive to negative. So when the derivative is positive, the slopes of the function are positive, so it's increasing. And then when the derivative is negative, the slopes are negative, so the function is decreasing, which means this turning point up here is a maximum at that critical point. So the first derivative test, when you need to justify this, we need to make a number line. Make sure this is labeled. You must label your work. I am labeling the top as the derivative, so I am saying that the derivative is negative and then the derivative is positive. On the bottom, I'm talking about f of x, so that if my derivative is negative, my function is decreasing. If my derivative is positive, my function is increasing. Now notice, if we decrease and then increase, it makes sense that our graph looks like this and we have a minimum. So what we would write on a test is f has a relative minimum when f prime of x changes from negative to positive. Okay, let's take a look at the other example here. So again, my top is labeled f prime of x. I show that the derivative is positive and then it's negative. Well, the bottom is going to be for my function. If my derivative is positive, my function's increasing. When my derivative is negative, my function is decreasing. And it makes sense that if we increase and then decrease, that we have a relative maximum. So we would write f has a relative max when f prime of x changes from positive to negative. Okay, so far so good? So here's a graph example, okay? So here's a graph, and I'm going to put a number line right underneath it, like this, okay? Let's put f prime of x on the top, f of x on the bottom, and we've got A, we've got B, and we've got C. Now this is the graph of f of x, okay? So that's this part of the graph. Now this graph is decreasing, right? At the beginning, we can see that it's decreasing. And notice all these slopes are negative, aren't they? All the way down here to A. They're negative, so we have negative slopes until we get to A. Then, between A and B, my graph is increasing, and you'll notice we have positive slope, positive, 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 positive slopes, right? Positive slopes, and my function was increasing. Then you'll notice that our function is decreasing again. Decreasing, 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 where we have negative slopes, which means our derivative is negative. Then we're looking, when the x's are greater than c, our graph is increasing again, right? And if we look at this graph, we've got positive slopes going up, going up, going up, going up, going up, going up, going up. Positive slopes means a positive derivative. So there's several things that we can say here. We can say that this graph, f of x, is increasing for a less than equal x less than equal b, and the x is greater than or equal to c since f prime of x is greater than or equal to 0. We can also say that f of x is decreasing for the x is less than or equal to a and b less than equal x less than equal c since f prime of x is less than or equal to 0. So these two statements are how the justifications will look in a problem. Now, we can also make a number line, this time with the second derivative on top and the function on the bottom. And if we look at this graph, it starts out all curved up till right about here. And let's call that letter D. So we know that our function is concave up till about what we're calling point D. And if our function is concave up, that means that our second derivative must be positive. Then our graph is concave down all the way till right around here. And we'll call that x value, let's say, E. So our graph is now concave down until we get to E. And if our function's concave down, our second derivative is negative. Then we go back, and now our graph is concave up again for the rest of time. So we're concave up, which means that our second derivative is positive. It also means that we have a point of inflection at D and a point of inflection at E. And we would say that f of x is concave up for x less than D and x greater than E, since f double prime of x is greater than 0. Notice we are not including the critical point of the second derivative here. We can also say that f of x is concave down for D less than x less than E, since our second derivative is less than 0. We would also be able to say that we have a point of inflection at D since the second derivative changes from positive to negative, and we have a point of inflection at E since the second derivative changes from negative to positive. Next, we have the second derivative test for max and min. This is a very important test, and it can be very useful and very helpful for us. This is another way to test for max and mins. So, if we know that the derivative of f at an x value c is 0, we know we have a critical point, which means we have a possible max or min. But we do have a horizontal tangent line. But if I put that together with the fact that our second derivative is less than 0, if our second derivative is negative, that means that our function is concave down. So when I think of a concave down function, it's going to have a horizontal tangent line at the top, right? That's where the slope will be 0. That means that we must have a relative maximum at x equals c. Okay, so if we know that the derivative is 0 and the second derivative is negative, we have to have a local max. Now let's look at another one. If we know that the derivative is 0, so again, we have a critical point, which means we have a possible max or min. And if we know that the second derivative is positive, that means that f is going to be concave up. So if I draw a concave up curve and I look for the point where I will have a horizontal tangent so that the derivative is 0, that's going to give me a relative minimum. So if we know that the derivative is 0 and the second derivative is positive, we must have a local minimum. Now, when can I use the second derivative test? If you know that f has a critical point, okay, at x equals a, which means that the derivative is 0, the tangent line to f of x must have a slope of 0 at that x equals a. You cannot use this when it's an undefined slope. It has to be that the derivative of f at a is 0. So it's not just any critical point. And also, you need to know whether the second derivative is positive or negative. If the second derivative is 0, the test is inconclusive. You can't get an answer for this. I will tell you that this test is very useful with optimization problems. This is when we start using applications of the derivative into real-world situations and word problems. This is when that test becomes very helpful. But let's take a look at an example, okay? So we have g of x is 2x squared minus the natural log of x for x greater than 0. We're going to identify the x value of the critical point of g of x, and we're going to classify the point as a relative, maximum, or minimum, or neither, using the second derivative test. So we've been told we have to use the second derivative test. So let's start with our function g of x is 2x squared minus the natural log of x. So the first thing we need is the derivative of g. So the derivative of g of x is going to be 4x minus the derivative natural log of x, remember, is 1 over x. Now, I don't want to know when the derivative is undefined. This derivative would be undefined when x is 0, but notice x equals 0 is not in the domain, so we don't have to worry about it anyway. So for our critical point, we're looking for when g prime of x equals 0, which would mean that 4x has to equal 1 over x. And if I solve by multiplying both sides by x, that means 4x squared equals 1, or x squared equals 1/4. Now if I square root that, I do not get 1/2. I get a positive or negative 1/2. However, I do know that x has to be greater than 0, so the critical point we're looking for is x equals 1/2. Now we know that g prime of 1/2 equals 0. So let's rewrite this derivative, which was 4x minus 1 over x, remember, is x to the negative 1, because now I need the second derivative. So the second derivative of 4x is 4 minus the derivative of x to the negative 1. I multiply by a negative 1, so that's positive, but my new exponent is a negative 2, so this second derivative is 4 plus 1 over x squared. Now to use the second derivative test, I need to find out whether the second derivative at this critical point is positive or negative. So we're going to do 4 plus 1 over 1/2 squared. Now, we can go through and do this arithmetic, because that's going to be 4 plus 4, which is 8. But you could look right here and know that this is a positive number, right? Because you have 4 plus a positive 1 over a positive number being squared. You know that this is a positive number, which, remember, means that our function is concave up, which is going to give us a relative minimum. So now we're going to write that up. So therefore, g has a relative minimum at x equals 1/2, since the derivative of g at 1/2 equals 0, and the second derivative of g at 1/2 is greater than 0. The next thing is I want to bring you back to the extreme value theorem, and we're going to talk about the candidates test. The extreme value theorem says that a function that is continuous on a closed interval absolutely positively must have an absolute maximum and an absolute minimum value. If you have a start and a stop and the graph is connected, you have to have a highest point and a lowest point. That's the extreme value theorem. Now, the candidates test tells us that to find the absolute maximum and the absolute minimum, we need to check the locations where they could occur. The only candidates for an absolute maximum and a minimum are the critical points, which is when f prime of x is 0, or when f prime of x fails to exist, which means the derivative does not exist, right? Just dne. Those, remember, are the critical points. Or the other place the maxes and mins can happen are at the endpoints of closed intervals. And this rule only applies when you're on a closed interval. But if you have a closed interval, you have to have an absolute max and a min. So let's take a look at an example. Let's draw a function. Let's say it starts here at a, and we're going to go, let's see, we're going to go up, then we're going to come low, going to go up, low, and let's go way up here. And that point, oh, look at that, we're going to end right about b, okay? Good. And this is our function f of x. And I want to take a look here. So we are definitely on a closed interval, f of x, on the closed interval from a to b. And if we take a look here, we have an absolute maximum here at this endpoint, and we have an absolute minimum here. Okay, but what about relative maxes and mins? Well, here's a relative max. Here's a relative max. And here's a relative min. Now remember, relative maxes and mins, for a relative max, the derivative had to change from positive to negative. For a relative minimum, the derivative had to change from negative to positive. That means that you cannot have a relative, or sometimes called a local, extrema, that means max or min, at the endpoints. You can only have absolute maxes and mins at endpoints. So how do we apply the candidates test to find the absolute extrema? First step is to find all the critical points. That's where f prime of x equals 0, or f prime of x does not exist. Next step, you're going to list the critical points and the endpoints in a table. You don't have to use a table, but it's a nice way to organize things for yourself. And then you're going to evaluate the function, that's the original function, at all those x values you found in the step above, and select the answer. Whether you're looking for the max, you take the biggest value. If you're looking for the min, you take the smallest value. All right, guys, we're going to stop here for today because we've done an awful lot. We reviewed how to find when a function is increasing or decreasing, when it has maxes or mins. We looked at when a function is concave up or concave down and what a point of inflection is. We learned the second derivative test for finding maxes and mins. And then we looked at the extreme value theorem and the candidates test. Have a great day, guys. Bye.